Welcome to this video. In this video, we will be looking at a few practice questions on uncertainties of measurements. In the first question, we're told that we got a particular reading in an experiment, and it shows that s is equal to 2.8 plus or minus 0.2 meters, and t is equal to 0.68 plus or minus 0.05. Note that these are nicely written because we have the same number of decimal places in the indicated value and the uncertainty in both cases, and our uncertainty is also written in one significant figure. In order to figure out the max and min values, I'm going to add 0.2 to the first one and subtract. So I get 3.0 and 2.6. And for the second one, I will get 0.68. If I add 0.05 to it, I will get 0.73. And if I were to subtract 0.5 from it, I will get 0.05 from it, I would get 0.63. So those would be my max and min values. In the next question, we got Mr. Shateri, who records the time taken for the paper airplane to drop as 4.56 plus or minus 0.01 seconds. He used his smartphone timer to manually time the intervals of the drop by pressing the button at the start and end of the flight. Explain, justify if the uncertainty is well recorded. Well, in this particular case, there is instrumental uncertainty and there is technique or procedural uncertainty. The instrumental uncertainty is the smallest increment here, which is plus or minus 0.01. The technique uncertainty comes from his reaction time, which is on average about 0.25 seconds. So I'm going to round that to one significant figure. About 0.3 second, and whenever we're doing a measurement, we will have to take the maximum value between the instrumental and anything we do in terms of technique or procedures. So in this case, we actually should use plus or minus 0.3. So the proper way of expressing this value would be 4.56 plus or minus 0.3. Oh, but wait a second. This has one decimal place, and this also needs to have one decimal place. So proper way, and the correct answer, I have to round this to 4.6 plus or minus 0.3 second, and that would be my final answer. So in an assessment situation, you do want to mention that these are the instrumental and procedural uncertainties, but we do need to take the maximum value, and in this case the maximum value comes from the reaction time, and therefore that's the one that needs to be chosen, and those will give you kind of communication marks and a little bit of thinking marks and application of your knowledge to the questions. And you also need to have that final value in there. I'm going to zoom and I'm going to move the page. In the next question, we got Mr. S has designed a trebuchet and has measured the horizontal distance that the cannon travels at an angle of 20 degrees distances as 48.2 meters, 51.3, 50.0, and 47.5. Determine the average, absolute, and percentage uncertainties of the measurement. Starting off with the average, that's going to be approximately 48.2 plus 51.3 plus 50.0 plus 47.5. We're just taking the mean or the average, and we're going to divide it by 4 because we have 4 trials. When I put all of this in my calculator, I get 49.25, so I'm going to keep it as that for now. For the absolute uncertainty, I am going to use this method of max minus min divided by 2. So I'm not using standard deviation here. And I will get my maximum value here is 51.3 and my minimum is 47.5. I'm going to divide it by 2 and I will end up getting 1.9 as my final answer. The units for both of these are in meters. And finally, for my percentage uncertainty, I will just take the 1.9 and divide it by 49.25 and multiply by 100% to get approximately, and these are all approximate coming from the measurement, at about 4. This would be approximately 4%. So in order to write the measurement properly in terms of the uncertainty and the average uncertainty, this one over here needs to be the uncertainty always one significant figure. There's some rules in which you can kind of change that, but for now we're going to change it to that. And since this will then have only it will have no decimal places, that would mean that for my measurement I will get 49 plus or minus 2 meters as my final answer, with a percentage uncertainty of approximately 4%. If this was being marked in an assessment, some of the steps that I will be looking for is this step here. I want this step here showing that the numbers are plugged in. I want numbers plugged in here, the final percentage and the final value here. Those are the necessary steps. Anything else there could achieve some part marks. For the next question, we got Mr. Shateri is measuring the speed of a soccer ball kicked by a soccer player under controlled conditions. He measures the value 3 times at 20 plus or minus 0.5, 25 plus or minus 0.5, and 18 plus or minus 0.5 meters per second. And the uncertainties he measured were based on the instrumental uncertainties. Determine the percentage uncertainty of each measurement. To find the percentage uncertainty, let's call the first one A, next one B, next one C. So percentage uncertainty of percentage uncertainty of A is going to equal to the uncertainty divided by 20 multiplied by 100%. Percentage uncertainty of B is going to equal to 0.5 divided by 25 times 100%. And these are all estimations because they're measurements. And percentage uncertainty of C will be 0.5 divided by 18 times 100%. The values here will be approximately 2.5%. Here we will get approximately 2%, and here we will get approximately 2.7 or 2.8%, or you can just write it as 3, and for the first one you can also just write it as approximately 3%. Now, determine the average, absolute, and the percentage uncertainty of the 3 trials. We can definitely do that. Actually, for the main steps here, things plugged in, and the final answers are what will be looked for. They could be full marks, there could be half marks, depending on the situation. The average, absolute, and percentage uncertainty, very similar to last time. For the average, I am going to take the values, add them together. And I did 3 trials here, so I'm going to divide it by 3. And I will get approximately 21 meters per second here. And then my absolute uncertainty, just going to write it as sigma. I'm going to take the max value minus min value divided by 2. So my max value is 25 minus 20 divided by 2. Sorry, that's minus 18. And I should get 7 divided by 2, which is 3.5. So I'll leave it as that for now. And my percentage uncertainty is going to equal to 3.5 divided by 21 times 100%. And that would be approximately 17%. So given all of these, I will also make sure I have the units here. My measurement would be 21 plus or minus 4 meters per second with uncertainty of 17%. And the reason why I have this plus 4 is because the uncertainty needs to be rounded to one significant figure. So that's good. And finally, the last question says, compare the results. Do you believe that there are any uncertainties due to the technique that Mr. Shateri may not have considered when he was recording his initial values? Well, I'll talk about this one a little bit. We can see that from the initial question, it's right here. The uncertainty of each individual value was about 3%, somewhere between 2 to 3%, but when we combined everything together, we are getting 17%, and usually repeating experiments will actually reduce random errors. So what might have happened here was a procedural uncertainty that happened due to some reason that Mr. Shateri wasn't thinking at the time, because these are all instrumental uncertainties, which are 0.5. So Mr. Shateri probably didn't take something into consideration. It could have been the position of the camera. Maybe it was moving around each time. Maybe it wasn't as controlled as he thought. So these numbers should actually be a little bit higher in order to properly show the uncertainty of each individual values. And during that procedure, something went wrong, and Mr. Shateri was just not able to properly measure it with that much certainty or that much uncertainty. So it was much more uncertain than what he initially thought, and that's why you can see that after actually combining all the values, the error has actually increased. If these were properly recorded, then what would have happened is these uncertainties would be much closer to this or usually larger, because by repeating the experiments, we often reduce the random errors and we don't usually increase them. Okay, that being the answer to C, the full, there's the explanation, another explanation down in the solutions if you want to look at that. We're going to move into random and systematic uncertainties section. In this particular question, Mr. Shateri measures his mass on top of a mountain as 75 plus or minus 1 kilogram. He's quite surprised about this value as it is lower than usual. He repeats the measurement 3 times and gets the same value within the uncertainties. Outline if this is an example of systematic or random uncertainty. So, wrong wording here. We're going to use uncertainty. And in this case, I'll explain these ones. The full solution is on the back, so I don't want to be writing. But in this particular case, what is happening is after repeating the experiment, the values don't change and the uncertainty remains the same, meaning that it's definitely not a random uncertainty. So the other problem, if he, before coming here, let's say he measured his mass and his mass was approximately, let's say 79 kilograms or something, and now he's seeing it as somewhere between 74 to 76, that would mean that his mass has decreased. A systematic uncertainty has to do with something where every time you make a measurement, it's always wrong by the same amount. In this particular case, if Mr. Shateri is on top of the mountain, very likely a up here, the gravitational acceleration acting on him is a lot lower than up here. So let's say here maybe the gravitational acceleration is approximately 9.8 meters per second. Up here, let's say it's about 8 meters per second squared. So it's a lot less. That would mean that the force of gravity acting on him is a lot lower. And if that's the case, usually as you go up in terms of altitude, that gravitational acceleration gets lower and lower, and you would feel lighter. And that's kind of exactly what's happening in this case. And therefore, every time he goes on the scale, it doesn't change the fact that the gravitational acceleration is lower in that region, and therefore he's going to feel much lighter. And because every time he does it is the same mistake, or the same amount away from the true value, therefore this is going to be called a systematic uncertainty. Question number 2 says, state the type of error that is reduced by repeating an experiment. So state simply means to write an answer without any explanation, and the type of error which is reduced by repeating an experiment is random uncertainty. Again, we're going to try our best to avoid the word error and use uncertainties instead. Moving on to the next question, we got Gerald, who is not happy with the result of an experiment. He knows that the actual value of his recorded data, what it should be. The teacher says that there may be systematic errors. He decides to perform more trials with the same equipment using the same techniques. He does not check the equipment for calibration. Explain if this eliminates the systematic errors. The solution, again, the more detailed solution is written later on in the document, so you can always check that. But in this particular case, repeating the experiment just like the last, or just like the very first question, only reduces random uncertainties. And those are the ones in which every time you do something, it gives you a different answer. So by repeating the experiment, Gerald isn't really helping this at all. So what might be happening here is the instrument that is being used, let's say it's a scale, we don't exactly know what it is, might not be calibrated. And if it's not calibrated, every time it's putting an object onto here, the measurement is maybe adding 0.5 kilograms to it. And what he needs to do is he needs to go and make sure that everything on the scale is properly adjusted, maybe connected to a certain software, and make sure that it's calibrated to 0. So when there's nothing actually on it, it's reading 0 kilograms. And once he calibrates that, it should be much better. So this would usually, if somebody repeats the experiment and keeps getting the exact same value, that would mean that it is not a random error, and that would mean that it's a systematic error, especially if you know what the answer should look like. So in this case, we have a systematic uncertainty and not a random uncertainty. In the next question, a student measures the width of an object several times and records the following data. We get 2.3, 2.4, 2.2, and a bunch of other ones. And then he decides to represent the data in the following way. So adds all the values, divides it by 7, gets the uncertainty by taking the maximum value, subtracting it by the minimum, and then dividing it by 2 to get 0.3, and records the value as 2.4 plus or minus 0.3. It looks really good, but then the teacher tells the student that his report should read 2.3 plus or minus 0.1 centimeters. Explain how did the teacher get this result and what type of error did the student commit. So this is a little bit of a thinking question in terms of what we've done in class, because we haven't really done something similar yet. In this particular case, the student has taken enough data to be able to tell if anything is an outlier. An outlier is something that's really far from all other results. So we can see that we get 2.2, 2.3, 2.3, 2.3, 2.2. So most of the values are between those, but we get this one which is quite far from everything else. And if this is the case, and if you have enough data to show that, if I only had value of 2.2, 2.3, and 2.8, I can't really tell what's happening, but having more data does allow us to get rid of outliers. We would have to remove this. So by removing an outlier, by removing the outlier, which is 2.8, our new average will become 2.3 plus 2.4 plus 2.2 plus 2.3 plus 2.2. I think there's a few of those. And we now have 1, 2, 3, 4, 5, 6 values. And I will get 2.283 repeated. So I'll come back and fix the final measurement in terms of proper number of significant figures. The uncertainty will be measured by the max value. The new max value is 2.4. The new minimum value is 2.2 divided by 2, and that's 0.2 divided by 2, which gives me 0.1. This is now in one significant figure, and I would have to round my other value, and this is 2.28. I made a boo-boo, and I will end up getting 2.3 rounded to 1 decimal place because of my uncertainty, and plus or minus 0.1 centimeters. So the mistake that was made was seeing all the values here. The student didn't recognize that this is quite far away from all these different values. And sometimes it's 2.8, it will be a hard one to kind of say it's an outlier because it's still close to the other values. It's not super far away. But it is a good idea to kind of look, and if you have enough data, and if all of them are very close to each other, and especially in this case, we got multiple values of 2.2, multiple values of 2.3, so we know that it's somewhere around there, and 2.8 is too much. If we had only 3 sets of data, we can't tell that because we just don't know what the other values are. So sometimes if you're getting data similar to this, where you have something which is much higher or lower than your other 2 measurements, it's not a bad idea to repeat for the 4th or even a 5th measurement to kind of help you a little bit more to be certain about the correct measured value. All right, okay. Let's move on to absolute, fractional, and percentage uncertainty. Determine the absolute uncertainty for the following measurement. So this is very similar to the last set of questions, so we'll do that. Absolute uncertainty would equal to my max value, 5.8 here, minus my min value, which is 5.4. And I'm going to divide it by 2. In this case, I will get 0.4 divided by 2, which would be 0.2, and that is my absolute uncertainty. For part B, we're asked to determine the fractional uncertainty, and so this is centimeters, so I want to include that. Fractional uncertainty would be the uncertainty of the value divided by the measured value. So we got to figure out the indicated value in terms of the average. So I'll do that on the side here. Average is equal to 5.8 plus 5.6 plus 5.7 plus 5.4 plus 5.4 plus 0.6, and we have 6 values. And once I do these measurements, I get 5.583 repeated. This is actually asking for the fractional uncertainty and not the percentage. So this is fractional. So just divide this by 5.583. And I will get approximately 0.0358. And for number of significant figures, this is a little bit challenging for this. I'm usually okay with you leaving it in this many, but I would usually go based on the original set of numbers, and I would put 2. So for fraction, I would put 0.036, but doesn't make a huge difference. And it's a fraction, so meters divided by meters, we will have no units for that fractional uncertainty. For the percentage uncertainty, basically, we have the fractional one. We just multiply it by, so I'll just do 0.358. The number continues here, times 100%. And we would get 3.6% approximately. I'll just bump it into 4%. That's the approximate percentage uncertainty. In the next question, we're asked to determine the area of a rectangle measuring with, I guess, width and length of 1.2 and 1.7 plus or minus 0.1. So let's do this. I'm going to bring this up, and I am going to use W and L for width and length, and this would be the uncertainty, and this would be the uncertainty. So for the area, it will be length times width, and that's 1.7 times 1.2. My calculator, that gives me 2.04 units will be meters squared. In order to figure out the percentage, in order to figure out the uncertainty of the area, I have to look at what operations I used. I have 2 measurements and I'm multiplying them. Whenever we multiply or divide 2 measurements, we need to add their percentage uncertainties. So the percentage uncertainty, or the fractional uncertainty of my area will equal to the fractional uncertainty of my length plus the fractional uncertainty of my width. So I'm going to do that right here so I have a little bit more space. The uncertainty of my area over the area value, we already calculated that as 2.04, will equal to the uncertainty of length is 0.1, length is 1.7, uncertainty of width is 0.1, width is 1.2. So I'm going to put all of those into this equation, and I will get 0.1 divided by 1.7 plus 0.1 divided by 1.2. Alright, so I will have that fractional uncertainty here. I'm going to put that on my calculator, and I'm going to get 0.14215. I'm going to use the exact value. I'm going to multiply this value by this in order to get rid of it from the left-hand side, and I will end up getting that the uncertainty of the area is approximately 0.29. Now, in order to write the proper measurement of my area, I will have to first of all round this down to one significant figure, giving me 0.3. And then I would have to change the number of decimal places for this so it matches that. So my uncertainty, therefore, is going to be 0.3. Unit is meters squared. And my 2.04 is going to be rounded to 2.0 in order to have the same number of decimal places as my uncertainty. And that is my value there. In the next question, we're asked to determine the value of 1.5 plus or minus 0.2 meters to the cubed. So it's just kind of like taking a volume of a cube. And basically it means that we're multiplying the length by itself 3 times. So let's do that. I'm going to say that length here is equal to 1.5 and the uncertainty of length is equal to 0.2. And let's assume that we're finding the volume at the end. So for the volume, the uncertainty of the volume over the actual volume value is going to equal to the uncertainty of length over length 3 times, because we are multiplying it by itself 3 times, because we multiply it once again to figure out this value. And I'm just going to write that the volume itself is equal to length times length times length. And this is going to equal to, I'm just going to put it on my calculator, 1.5 cubed, 3.375. So I'll put the values in. I get 3.375. Uncertainty of the volume is going to equal to uncertainty of length over 1.5 plus. And you can also just write this as multiple of, you can just write this 3 times this, or just the exponent multiplied by this. It'll be the same idea. And where did my, okay, there we go. We get the fractional uncertainty will equal to 0.4 when we add all of them together. And if I multiply both sides by 3.375, I will get the total uncertainty, actually pretty large, 1.35. And the units here is meters cubed. So then the final measurement, I will need to take my uncertainty and turn it into one significant figure. So plus or minus 1. And my value, I need to also have no decimal places for it. So that's going to be 3 meters cubed. And that is my final measurement. Alright, finally, the width of a calculator is being measured. 2 measurements at the 2 ends of a ruler are 3 plus or minus 0.5 and 19 plus or minus 0.5 centimeters. Outline a mistake in the recording of the measurements or measurements. So in this case, let's check for everything. We got our uncertainty is 1 decimal place, and, or sorry, 1 significant figure and 1 decimal place. This is 1 decimal place. No spacing between, okay, I'll just write it like this, and I'll just say that this should be written as 3.0 plus or minus 0.5 centimeters, where there needs to be a space between the measurement and the units. For my next measurement, I have 19 plus or minus 0.5, so 1 significant figure for the uncertainty is great. This is 1 decimal place, this is not, so that would mean that our second measurement should be written as 19.0 plus or minus 0.5 centimeters. So that's the other mistake, the fact that we don't have the decimal point here. Next, determine the measurement for the length of the ruler using proper notation. So let's draw this out actually so we know exactly what's happening. So one of the measurements we made was here, 3.0 plus or minus 0.5. The other measurement was 19.0 plus or minus 0.5. And let's say this is the width of our calculator. So in order to find the length, I have to subtract the two. So length will equal to 19.0 minus 3.0, which should equal to 16 centimeters. So that would be the length there. In this case, I am subtracting two values. They both have one decimal place, so my final answer should have one decimal place when I'm doing the proper notation. Determine the... Oh, but we need the measurement, and in order to get the measurement, we also need the uncertainty. So to find the uncertainty, since we are adding the two values, the uncertainty of the length is going to be equal, or the width here. It is definitely the width. Okay, I'm just going to change this to W and this to W. The uncertainty of the width will be the addition of the uncertainty of the two values. So it's going to be 0.5 plus 0.5 because uncertainty of this one is 0.5 and the uncertainty of this one is 0.5, giving me a total of 1 centimeter. And I'm going to write it as 1.0 here. But when we're writing the when we're writing the measurement, we need to change our uncertainty so it only has one significant figure. So I'm going to change it to 1. My unit is centimeters. And my width, I'm going to round it to no decimal place because now this has no decimal places, and it's going to end up being 16. So I'm going to highlight this, and this is going to be my measurement. Finally, determine the percentage uncertainty of this measurement for part C. So percentage uncertainty is going to be the... Actually, I'm going to write it this. It's going to equal to the absolute uncertainty divided by the width multiplied by 100%. And when I do this, I get 1 divided by 16 times 100, which will be approximately 6%. What I would be looking for in these types of questions is, first of all, the mistakes need to be mentioned properly. It's an outline question, so you need to say what the actual solution should be, and you need to talk about why it's the case. So those are kind of 2 marks for the explanation needs to be there as well for each one. For the second one, determine the measurements. So you would want to show me the uncertainty calculation, the subtraction, and my final value. Some would be half marks, some would be full marks, but you need to show those steps. And for this one, you need to show, I guess I didn't do this really well. I'm going to erase it and show all of these steps. 1/16, I'll write it in red because I didn't write all the steps initially. And this is going to end up being approximately 6%. So I'm looking for the values plugged in and the final answer. So those are some of the steps that I'm looking for. We go back to these types of question. Also, I am looking to see numbers plugged in, final value, numbers plugged in, or the final value. If it's easy enough of a calculation, sometimes it's okay to avoid those, but try to plug in the values as much as you can in order to show me that you know what you're doing. And those are some of the necessary steps that I'm looking for. Numbers plugged in and the final values as well, properly rounded to the correct number of significant figures. The final question here is actually a repeated question, so you don't have to repeat it. And if you need to see some of the solutions to the previous questions with more descriptions, you can see them here so you have a better idea, because I kind of explained it in the video, but I didn't take the time to write them. So these are some of the answers to some of the previous questions. If you need to go back and check them out, these would be kind of what I'm expecting when you're answering the questions. I hope that this video was helpful for you, and have a wonderful, wonderful day.